Okay, might as well get started. All right, Wednesday, April 16th. So do you guys know there's like 3 lectures left, right? There's there's today, there's next Wednesday, because we have a holiday Monday, and then there's the following Monday, and that's it. The Monday class will be the review class. So we'll talk about what's going to be on the final, what you have to prepare for, et cetera, et cetera. Today's class is going to be kind of on it's on these things called containers, which we've already done a little bit about, and templates, which we've done, and I'm going to talk about vectors. I haven't yet planned out next Wednesday's class. I've got a couple of ideas, though. Raise your hand if you're taking Comp 40 next year or at some point in your future. OK, if you're not, you can laugh. Yes, I see that. What I might do is on next Wednesday have like how to prepare, what you need to know to do well in Comp 40. Something like that, which would be basically, here's the C language and some of the differences between C and C++. Here's how you do bit shifting and bit manipulation, a couple little things that you'll need to know in Comp 40. Now, that does not mean that those of you who are not taking Comp 40 won't get anything out of that class either, but it's not really necessarily going to be geared towards you, if that's all right. What it kind of means is, you'll see a little bit of the pain that you might not have to deal with. But that's one idea. I'm also thinking of possibly doing a couple other data structures we haven't yet talked about, but I'm still thinking about it. If you have comments about that, if you'd really like to do what's going to be necessary before you get to Comp 40, put something on Piazza or something, and maybe we'll start a little thing there. And then otherwise, if you say no, I'd rather do something that's more data structure itself, then we'll do that. But that's what I was thinking about. The labs next week will be a little different too, because Monday doesn't happen. So Tuesday and the following Monday, it'll be our last lab. I don't think we'll actually do a lab in particular, but we'll be filling out like course evaluations and doing and working on projects. So we should be able to get some of the things done there. OK, questions before I get going? All right. So today, oh, actually, I forgot I didn't put a Unix tip of the day, but somebody yesterday was asking me something, and then the conversation ended up going, hey, you should do a Unix tip of the day on this. Yeah, question. Oh, how do you provide the plan? You do, let's see, you do make provide underscore design, I believe it is. It says how to do it in the document I handed out, but that's how you do it. And then it should do it. Yeah. So yesterday somebody came up and has anybody ever lost any files on your computer or like deleted a file accidentally or whatever, right? Like common stuff. I keep everything in Dropbox, so Dropbox saves a lot of my stuff for me. But if you're on the server and you delete something accidentally, or if you write over a file that you didn't mean to, and that happens a lot, there is actually a .snapshot folder. Some of you guys are going, yeah, I know all about that. In your main folder, if you look at your main, like this is my main folder, chgreg. In there, if you do cd.snapshot, right, it actually goes into another folder that has a list of hourly backups, and then nightly backups, and then weekly backups, right? So your stuff is, now it's not really every hour your stuff gets backed up, but it's more or less. The stuff that says hourly 0 is the latest stuff that got backed up, right? And if you, within a week, if you realize that there's no monthlies on there, are there? No. If you realize within a week that you deleted something, you can probably get it back, right? Because what you do is if you go into, say, hourly.0, it is all your files. Those are all the ones that you, like you can go to desktop now, right? And there's all your desktop files. I don't have a Comp 15 or whatever, but if you go in there, the files that you deleted, the files that were in there yesterday or an hour ago will still be there, right? And then it gets replaced and everything propagates through, and then a week later, the last one gets pushed out the other side. So it's a backup system for your stuff. And it's really nice if you all of a sudden are working on a project and something gets deleted. Or let's say you're going down some path and you realize, you know what, this is a terrible idea. And I didn't figure out how to like save the stuff. And I want to go back to what I worked on 2 hours ago. Just go back into the thing. You may be able to find the stuff you worked on 2 hours ago. and get it. And then you can just copy it into your main folder or other folders wherever you want. Okay? So it's kind of a cool idea. Questions on that? Nice little backup system. Yeah. All right. Oops. Oops, there we go. I'm going to go back here for one sec. See, there we go. All right, so let's talk about, here's what we're going to do today, by the way, vectors, templates, and what actually templates are. The reason I'm going to talk about this vector thing is because it actually may help many of you in your song search project. And by the way, when we get done talking about vector, you can ask any questions you want about song search and so forth. Any other questions are fine. But the vector container is just like the queue or stack containers we've used in lab a couple times. And what it is it's what we call a wrapper around a dynamic array. So if you have elements you're trying to put into a dynamic array, instead of building your own dynamic array class or object where you have to do the dynamic, like expanding and all that, this does it for you. Right? Here's kind of the motivation for, well, that's what the vector itself will do. Okay? It being able to store any type of object is the powerful part about it. So if you want to store structures of your songs and frequencies, if you want to store strings, if you want to store characters, you can do all of that in these containers. Okay? And these containers actually come from what we call the standard template library. Okay? Here's kind of a little motivation on this. All right. You have a container, right? Containers in real life in general aren't necessarily made for one particular object. Now that's not always true, right? If you get a box and it comes like, Apple's like famous for this, right? Their boxes are like perfectly designed for their exact, iPhone or whatever it is, right? And everything fits perfectly in there, right? And that's really the only thing that would go in that box, in that container. That's an example of a very defined use of a specific container. What's another one I was thinking of? You ever see, you guys know deviled eggs, right? There's like little containers that you like put deviled eggs in, and each it's got a bunch of holes and they're egg shaped and they fit eggs, and you can put like down, you give a plate and you go to a fancy party and they hand you one. It's like, but that's a very specific container. That is not, you wouldn't want to store like ice cubes in it or something, right? Although that would be kind of cool. You'd have a half egg shaped ice cubes. That would be kind of neat. Anyway, in real life, we try to store stuff that we try to make containers that will store lots of different things. Okay? So shipping containers can hold toys, they can hold auto parts, or they can hold like illegal drugs or whatever, right? But they can hold lots of different stuff. They can actually hold stowaway kittens, right? This one I found, that cat got all the way from the Philippines to Los Angeles. Does not look too happy. And I can imagine it wasn't particularly fun for the cat. First of all, I was like, what's going on? For like 3 weeks, right? Luckily, ships are pretty fast. But anyway, so containers, you want them to be able to hold multiple types of things, right? And that's what the goal of the standard template library is. And some of you guys already know about all this stuff, but I want to just kind of dig in a little bit, especially at the end here. We'll go into more details about like how you can build your own template libraries and things. Okay? So the goal of the standard template library is you have these functions, or these classes really, that have the ability to store any kind of object you throw at it. If you want to store hashes, or you want to store strings, or you want to store class objects, or doubles, or structs, or whatever you want, they should be able to be handled by that container object. And by container, I mean the data structure object that we've been talking about, whether it's a queue or a stack or in our case, a vector that we're going to talk about. In a queue, you know something about a queue, right? You know that you can get the front element. You know that you can push and it goes on the back, right? You can in-queue onto the back of a queue and you get the object off the front. Those are generic ideas, right? And they're generic in the sense that you don't care if you're pushing on an int or a float or a class or a song or a structure of some other sort. It doesn't actually matter, and that's the whole point, that you want the container to be able to do this, right? So if we want a queue of floats, we're just going to use floats. Yesterday in class we used a queue of integers, right, when we had the lab. we used a queue of integers and pushed on integers. Some of you tried to use a queue of Boolean values. That actually works perfectly well too, right? But the idea is make a container, have it meet the requirements of being able to do its function for any kind of object. All of these guys, right? So it's kind of a neat idea. And it's not a particularly, like, it's not a really old idea either. It's like when people were thinking about first programming in writing programming languages, they didn't really think about it this way. Objects didn't really exist. Types, of course, existed. But if you wanted a queue of floats and you wanted to build it, you'd build it for floats. If you wanted a queue for integers, you'd build it for integers. And it's like what we've done in most of our class here. You have a very specific type that you're throwing in, and you build it around that type. We want to make it more generic. Okay? We've seen queues and stacks. We've been storing integers. We can store whatever we want. Okay? That's the whole point. And this thing called the standard template library is given to you. If you have a C++ compiler, you should be able. It should come with this standard template library, which has all these great containers and other objects in them, like queues and stacks. So you don't have to go build them. What's one good reason for you not to build your own queue? I can tell you why I wouldn't want to do it. Yeah, Marcus. It takes time to build your own queue. You want to just do the queue. You want the queue function. You don't have to build your own. What's another one? Yeah. You could have a small stupid bug. Yeah. Number one, you could have a small, like, the people who create the standard template library, they have tested this like as much as they can. Like thousands and thousands of people have already tested this, so it probably works. Not only that, it probably works as efficiently as it can. So not to say you guys don't write efficient code, and that's the whole point of this class, is to write efficient code, right? But a lot of times you'll have a little, you might iterate through one extra element when you don't really need to, right? Sometimes you don't need to worry about that first, like the 0th element, because you're comparing against the next one. But sometimes you just say, it's no big deal. Well, the people who write the standard template library have thought of all of that, right? So they've made it really, really efficient, okay? The other part, again, of course, is that's built for you. Now, part of the reason, the main reason you could say that we built a lot of these things ourselves is so that you'd understand them, right? And you'd understand when to use a queue and when to use a stack. But point is, these are already built for you. If you know when to use them, great. Vector, you don't want to use a vector when you're doing lots of linear searching and so forth, that sort of thing. So these are the ideas you should know by going through this class, right? OK, so that's the types of classes that are included in the standard library. Okay, there's also a priority queue. There's vectors, as we said. There's sets. There's maps, which are kind of like, they can be either hash tables or like binary search trees. But there's lots of different things in the standard library. Okay, and again, I'm hammering this part. You can store any type in them. This is the important part. Okay, questions so far? What we're doing with these? Okay, let's talk about why this actually works for a second. And then we're going to go into more details a little bit later. The standard template library classes have this thing called compile time polymorphism. All right? Polymorphism is a really interesting idea. What it means is that you can take one class and you can say, OK, I'm going to build it specifically for ints. I'm also going to build it specifically for floats. I'm also going to build it specifically for strings. And it means that you can take that same object and apply it, poly, right? You can apply it to a whole bunch of different types of objects. The compiler actually does that. It turns out that the C++ compiler actually has another compiler built into it specifically to do the compiling of these standard templates or these templates. Okay, it's like kind of like a whole another compiler. It's actually a whole other programming language in itself. You can kind of think of it like that. And it's been like shoved into C++ so that we can do this stuff. Okay? What the compiler does is it says, OK, I'm trying to make a dynamic array of integers. Well, then I'd better create a dynamic array that is made of integers. And when I walk through the integers, I'd better go one integer at a time instead of, say, one structure at a time. And the compiler has to think about all that and builds your code specifically for that. What's nice about this versus, say, in another language like Java is that it does this, it recompiles specifically for the type you're using and doesn't have to do that during runtime, so it's really fast. That's one of the benefits of this, is that it gets the job done and gets it done fast because it specifically goes and builds these things for your object. Okay? So you tell a queue to use integers, and the queue functions are then compiled internally to just use integers for that part of the program. You can have 2 queues in your program. You can have 100 queues in your program. 1 can be for integers, 7 can be for strings, 6 can be for characters, and they're all going to be built specifically for those types. Kind of cool stuff. Okay? Likewise for any other type you can think of. And that's the beauty of it. You can make classes and put them in there, and structs and pointers and whatever. Rose, you've got a question.
I don't understand how to use it when you get there.
OK. So, well, here's what. So when you say something like, let's see, my array equals new int 20, right? It's going to do this, and it's going to make an integer array of 20 things wrong, right? And it would be like int star a equals new int 20, right? OK, so you have to do that. Now, when you come along later and say, you know what, I actually don't want to put integers in there. I want to put floats in there, right? You have to go and you have to change all these things to say float. Now, at the beginning of the year, at the beginning of the class, we actually talked about how you can put this part of it like at the beginning of the program and then just change it once at the beginning. You can do that. But what's nice is the compiler will figure out you don't even have to do any of this changing at all. You have to you do have to say it when you're defining what you're trying to do, but you don't actually have to do that. And then the compiler goes and says, OK, I'm going to now base everything in the rest of your program on the fact that I'm using floats instead of integers. So it's really not different from yours, except that you can make it so that you don't have to go and redo all this. You write one class, and then all of a sudden it's good for floats and ints and characters and strings and all that. Okay, so that's the big benefit there. Okay, and that's why we can use queues for integers or floats or characters or songs or whatever. Okay, because somebody else built the template for it and says now you use this with whatever type you want. Okay, in fact it goes a little bit deeper than that. In fact, if we do the whole prepare for 40 class I was talking about on Wednesday, we'll talk about the fact that for Boolean values, it actually says, oh, I'm doing a Boolean value. I'm going to squeeze the bits down so that I don't need to use whole integer numbers to do it. It's actually kind of clever. But the idea is you don't have to think about that. Somebody's already done the design. Yeah?
If you use the standard library, would you be able to have your input be of different types? Or does the structure still only accept one type?
No. Oh, good question. Like you have one queue, and can you put an integer in one spot and then a float in the next? You can't do that in C++. Other languages, you can do that in other languages. Python's a very good one. You can have a list of stuff, and in each one it can be anything. The problem with that, it goes back to how do you know when you get it out what type it is? Like you've got to be very careful about that. Java, I believe, still allows you to do that to some extent, but not as they have these generic types now as well. Used to be that you could get an array in Java and you could put any object into any place, kind of like Python. But they've changed that now because it makes it harder to debug in the end because you can throw anything in there. But now, no, you can't. For these, you can't. You can't say, oh, it's going to be any type of object in each particular one. Good question. Yeah. Okay, other questions on that so far? OK. Let's go into the vector class. I promised some of you guys I'd talk about this in class today. The reason we're going to talk about vectors is because I think you will be very happy to use them if you use them for your song search instead of a dynamic array. You can do a dynamic array. We have built dynamic arrays, and that's perfectly fine. But you may want to include strings in one dynamic array, and then you might want to include song lists in another one, and you might want to include, and I don't want you to have to rebuild your dynamic array specifically for each type. This is why the vector's done that for you. Okay? We have to go into a little bit of detail on how to use it, right? A vector is just, as I said, just a dynamic array And all of the dirty work is done under the covers for you. Okay? So if you want to add an object to the array, well, you say push back, and I'll show you how this works. You push that up to the back of the array, and it says, oh, OK, I'm going to put it at the end of the array. And underneath the covers, it says, oh, am I at the end of the array already? Like, am I at the capacity? I need to expand it. And it does, and I need to copy. And it does all that under the covers. It's great. You can refer to an object. In fact, in a vector, you refer to an object exactly as if it were a regular array. So you have some vector. It's like your song vector, right? Song 0 is the first one, the first song in that vector. Actually, I think I have that exact example in a second. Okay. Whole point is handled behind the scenes. It's awesome. Here's some of the things you can do with it. There are lots of things. In fact, let me just bring up a web page here that shows this. Let's see. If I do vector C++, it should give me the reference. Here we go. The first link. It's already purple. Okay. And hopefully it'll come up. OK, so this tells There you go. This tells you all about the class. And by the way, it says it's a template. And it's part of the standard library, et cetera. Right? And it tells you all about it. And then it says, look, here's the things you can do with it down here. Right here. You've got, well, those are iterators. We'll get to what those mean in a second. Here you go. Element access. You can use the brackets. You can say something at the thing. We can get the front of it. You can get the back of it. You can actually get all the data at once. Right? You can push to the back of an array. You can pop from the back. You can actually insert in a specific place in the array. Right? In the vector, you can insert into a specific place. You can erase the whole thing. You can swap values. You can, I don't know the difference, clear versus erase. Not sure what the difference between those is. And then there are lots of other things you can do with this. Okay? So there's a ton of different functions. We're only going to talk about a few today, but you can feel free to look at the rest of them as well. Push back some value, and that value is whatever type you've created for that, or you decided to use for that vector. You say push back the value, and it adds the element to the end of the array. And by the way, we know that's relatively fast, right? That's an order 1 operation. And the way they build these structures, they try to model it so that that's an order 1 operation, unless you have to expand, but that's rare. Size gives you the number of elements. So if you do array, if you have your array song, and you do, let me grab a piece of chalk here. If you do song period size, parenthesis, it's a function, that will return the number of elements in the song. Right? It's easier than keeping some extra count of it. Yeah, Laura. It returns the number of songs in there, right? The capacity, believe it or not, you can get the capacity. Not that you ever need to worry about it. Like, the whole point is you don't need to worry about it. But here it is right here. You can get the capacity. There's a function that says capacity. Return the size of the allocated storage. You can also reserve storage if you know. This might be interesting if you know about how many types of objects you're going to store. You can reserve space. Yeah. It does not only make it just as big as you need, initially anyway. Go ahead.
So if you ask for the size and how many spaces in the array, does it give you the total size of it, or only
It only gives you the number of elements that are in it right now. Okay. Now, if you ask for the capacity, it will tell you the total storage amount.
Okay. So the size doesn't count then?
Nope. The size just counts how many things have I stuck in there so far. That's all it does. By the way, this is a kind of a cool one they have in the newest version of C++, shrink to fit. So let's say you're doing an array, let's say you're throwing songs into something, right? And you double the size, and then there's like that one, like that, and the last one that you put in doubled the size of it. All of a sudden you're wasting all this extra space, right? Well, if you do shrink to fit, it says, oh, all right, how many elements are in there? There's exactly this many. I'm going to reallocate, get another set of memory that's just that long, and then give back the extra that I didn't need. So it's kind of a neat idea. And it's, they added this to the latest version of C++, C++ 11. Yeah. You do have access to that if you want. I put a Piazza post on how to do that. You may, so unfortunately, it looks like the Clang compiler we use was not quite installed perfectly. So you probably want to go back to G++ instead of Clang++. Your error messages won't be as good, but it'll actually work. So that's the trade-offs, right? But you can use it if you want. I don't. You know what? If you wanted to use this for your hash table or something, if you had a hash table full of vectors, you could do that. You could also do that manually too. I mean, you could also, when you get done with all the songs, say, oh, how big's my hash table? Oh, it's this long. I only need it to be this long. Rehash everybody into a smaller one, and you're good. Yeah.
So I'm just thinking, if we have a vector of that's a hash table,
Yeah.
we have to rehash it every time that it expands.
You have to, yes, you do. So you're probably not going to want if you're building your own hash table, you will just use a dynamic array, like a regular old array, because you do have to worry about that. It won't, I don't believe it actually tells you when it's resizing. You could figure this out, although I think it'd be just as much work to use a vector to try to cram your hash table into that than otherwise. Yeah, but that's a good point. Good point, yeah. OK, other questions before we talk more about the other functions? OK, so there's the operator one, which I said just works just like this. This is an overloaded function. We've talked about those before. It means if the compiler sees your vector and then the bracket and then the number in there, it will go to that, give you that element. Okay, it's random access, just like all dynamic arrays. You can also do an insert. Okay, insert's a little bit different. You can't just insert the value. Okay, you can insert the value. You can't just say, here's the position I want. It has to be what we call an iterator. I will go over what that is in a minute, but it's a little bit, it abstracts away a little bit more of the position for you, and there's a reason they do that, so that you can't just try to stick it anywhere in memory. But it's a little bit different. We'll get to what an iterator does. Okay, but these are the big ones you would use: pushback, size, and operator brackets. Those are the big ones you would probably use for this. Here's another nice thing about the song search one. We are doing a lot of putting things into a database. We're not doing much pulling, removing from a database. It's not like I say, oh, search for some song and then remove it from the database. It's not like the calendar one where you have to extract elements and change it. So that's a little bit nicer. You probably won't have to do the erase or the remove or whatever. OK? All right. So those are some of the functions. Here's how you declare a vector. It's just like we declared a queue in class. You say, by the way, you do need, forgot about this, you do need to say pound include angle bracket vector, like that. That is necessary when you are doing this, and you need to be using the using namespace std, which we always do anyway, kind of like strings. OK, so here's what you do. You say, I need a vector. I want it to be of some type, and then the variable name. OK, creating a vector of strings. This seems like one that might be important in the next few days for you guys, right? A vector of strings called lyrics. Yeah, question, Emma. Or Laura, sorry. You give it a size to start. Good question. You can give it a size, but generally you don't. It generally has an initial capacity. I want to say the initial capacity is around 10 or a dozen or something like that, but it's not that big. But it will double as necessary. It's clever that way. Yeah, good question. Yep.
If we know that we're going to have to be storing however many can we go so that it doesn't have to double as often, because that will save some.
If you know how many you're going to store, yes. Now, for our assignment, we're going to test it on small database and a big database. So you're not going to know up front, right? And what you don't want to do, and this is kind of in general, you don't want to say, oh, I think it's going to be this big, and then all of a sudden have it small, and then you use 2 gigabytes of memory for the 9-song Rick Astley database, right? That's probably not the best way to do it. Now, if you have some scheme where you read everything in and then count as you go, and then all of a sudden you create your database, probably not the most efficient way to do it, but then you could say, oh, I know it's going to be this much. Now, does it take a long time to do this expansion stuff? Yes and no. remember, expansion doubles every time. So it's you don't expand that often. Like you expand at the beginning, you expand a lot. But then every time you double, like you have to get, again, twice as many before you double again. And then it's twice as many from that. And so you get to the size you need relatively quickly. But yeah, if you want to, I mean, that would probably help, to know a little bit about that. And trust me, when like Google thinks about these things, they're going, OK, look, we know we're going to get a billion things here. So they probably do some of that. Yeah?
So if they say we had like a class that contains the pointer to a vector of string.
A class that contains a pointer to a vector of string. Sure. So let's say you had a class, right? And it's going to be, I don't know, my strings or something, right? And then in the private variables, it's got a vector, just a string in there in your class. Oh yeah, pointer to a string, sure. String, pointer, a string. Yep. OK.
Using the vector doesn't change.
Nope, using the vector doesn't change it at all. As long as, well, for your class, you do need to consider the copy constructor and the operator equals overload if you are going to have misdirection, like other direction like that. In many cases, now you may have a string like, strings are actually OK, because strings will do the copying for you. But if you have some pointer to another object, that other object had better have a copy constructor and an equals overload, because then when it gets copied into the vector, it will not necessarily work. Now, you can put pointers in vectors, which is kind of cool too. So then you don't have to do all it's going to do is copy the pointer, and it's going to be very fast, and it's going to do it going to be nice, easier to deal with, and you don't have to worry about that much. But yeah, you would have to do it if it was your own class and some other class that you came up with. Okay, good question. Okay, anything else on how I'm declaring these? Okay. Here's how you might use a vector. This look familiar to anybody? Right? Maybe some of you guys have come up with this idea. You have a song structure, a struct of songs. I forgot the semicolon here. And you say string artist, that's artist name, string title, and then here's your vector of lyrics. Okay, it's easier than trying to figure out, oh, it's a dynamic array of lyrics. It's going to be handled all for you, which is cool. Okay? If you wanted to, you could take this whole thing and put it in another vector of songs. That's kind of what you're going to do if you do a hash table or a trie. You're going to have possibly a pointer to this. That's what I would suggest. A pointer to this in some other object. And it could be a vector, it could be a hash table, it could be a trie, whatever you've decided. Make sense, Marcus? Look at me like I'm crazy. I probably am, but this isn't why. All right. So anyway, here's the dynamic array. It's just the vector right there of strings. OK, so this could be your class. As you get a new word, you pop it into the lyrics for that song. Make sense? Hope so. All right. So here's how we're going to use it. Here's how we're actually going to do that. Let's say you get the word, and you say lyrics.push_back word. Right? That's all. That's all there is to it. Don't need to worry about expanding. Don't need to worry about the capacity. Don't need to worry about a lot of nice things that you would otherwise have to worry about. Because we've already made you build all those. I'm not going to make you rebuild them all. Okay? All right. How do you use it? Well, like I said, lyrics 0 is the first word in the lyric. Okay? There's other ways to get that first one as well. In fact, a function called begin will give you the first one. Well, it'll give you an iterator to the first one, which we'll get to in a minute. You can do the size as well. This will give you how many elements it contains. We've talked about that. Okay? And then you may want to walk through the list. Right? If you want to iterate through the vector here, you can do it the way we've kind of always done it. Right? You can say, all right, by the way, vectors hold elements in the size underscore t, the amount that, remember the size underscore t says it's basically an integer type that will allow you to store as much as you need for the memory system you're using. You could say integer here, like int. You might get a warning if you do that, because it's not an integer. It's actually a long or some other type that's not. This says, hey, arrays store the size of the pointers are this big. Okay, so you can use that. But it's the same idea. Once you have that, your iterator through, or your index equals 0, I is less than lyrics.size, I plus plus, and then you can take each one in turn, like that. So that's how you'd go through the lyrics. Okay, you're probably not going to, well, you may count them out like this, but you're probably not going to do that directly like that. Okay, but that's how you use them. Yeah, Barry. Yeah, if you use int here, right, it will probably work, but it won't necessarily, it will give you a warning that says, hey, it's not you're trying to convert a bigger number into a bigger number type into a smaller number type, and it's a warning. It'll do it for you, but it's a warning. Now, this will probably not be the case, but if you got more than 4 billion things in your database, an int wouldn't even work, but a size t might, depending on how it's defined in the language. Okay, but yeah, if you're going to use vectors, this is the size of the values that are kept in there. The size of the pointers of the values that are kept in there. So don't use int, use size underscore t. Otherwise, you'll have lots of warnings. So, yeah, Eliza.
Do you define what size t is at any point, or does it just figure out from this?
It actually is defined for you in the header files for things like vector and for other header files. Yeah, it's already defined for you. Yeah, so you should be able to use it straight away. Okay, good. So this is one way to walk through a vector. The way that we probably understand the easiest. Oh, sorry. Go ahead, Avita.
Would an unsigned int or a long?
I think it is an unsigned int, actually. Yeah, that would work too. So if you want to use an unsigned int, that's fine. Long would probably also work. Yeah. Yeah. But size underscore t will definitely work, regardless of the other ones working or not. Okay? So that's an easy way to walk through it. That's the way we might understand. Take a look at a different way to walk through a vector. Okay? We can use this thing called an iterator. And we talk about iterating through, and we talk about, oh, it's an iterator, and it's iterating through. But there is a very specific definition of an iterator for these containers. Okay? An iterator actually allows you to go through the container directly without having a specific number associated with it. It looks very similar, but it's not a number, and I'll show you what it means. But you don't have to use these iterators for the most part. You will for one thing I show you. You won't have to use them for walking through. As you get more advanced in C++, you'll probably want to start using iterators because A, they're everywhere, and B, it's really the preferred method for walking through an array. Let me show, or walking through a vector and other containers. Let me show you what I mean. Okay. So we're dealing with vectors of strings here. Okay? Vectors of strings, that is your type of the object that we're dealing with. It's a vector full of strings. In it has another class called iterator that is part of the vector string class. So it's like it's a class within a class. Okay? And, well, actually, it's not a class within a class. Sorry, it's a variable within the class that is based on this idea of being able to walk through things. Okay? So it's a variable in there. And what it is you can say, OK, here's this iterator. I'm going to call it the word. I'm not going to call it the index anymore, because it's not an index. Okay? And what it equals is song and then lyrics.begin. That says the first element in your lyrics. Okay? And it's, again, not an integer, but it's actually going to be a pointer to a word, as you'll see in a sec. You start with the first one, and you go until the word is not equal to the end. And end is not the last one. It's like the one after the last one. End means I have finished going through this array. There are no more things to deal with. Okay? So it's like the length of the array. It's like the one after the last one in there. That's what end means. Okay? So here's what we're doing. We're saying, OK, here's my iterator. It's going to be called word. Word starts at begin. and goes until end, and then we increment the actual iterator. That looks very similar to what we did with the index before, right? You've got it's a for loop, you've got a begin, you've got a conditional when you end, and then you've got an increment in there. Here's what you're actually doing. You're actually printing out, in this case, these are that's just an extra character, and then you are saying, give me what word is pointing to. Word is an iterator that points to some place in the vector. And it says, dereference that and print it out. Okay, and then I'm going to print this other character. Let me show you what it does. This is exactly the same thing, except that I didn't do the other angle bracket there. But let me show you what it actually looks like. Let's see, hopefully I have this up here. That's that one. I do not, so let me open it up. OK, here we go. Let's look at vector example. Oops. OK, let me push it down for a minute. So here's what we've got here. We have, OK, this is a word list. Let me see if I can't make it bigger for you. Lecture hall, how's that? There we go. It's a little bigger. It's a lot bigger, actually. OK, so here's what we've got here. We've got just a word list. And by the way, you can grab this off the web page, OK? If you're having trouble starting on this assignment, right, you might want to grab this and see how I've set it up, because you might be able to work this right into your program for this week. So if you're having trouble starting, this might be a good place. OK? In here, we've got a thing that says process word, current song, word, the print song. Here we go. So I've written it twice here. I've said the simple counter method, and I've got that highlighted out, or I've got that commented out. And then I've got the iterator method, which is exactly what we had in the previous page here. OK? It's going to go through the whole lyrics for a song and print out each one word by word with the little alligator things on each side, right? The less than or greater than on each side. OK? Watch what happens when I run this. Oops, it's not going to work because I was doing this on a different computer. Hold on one sec. This is what happens when you try to work with two different computers. Luckily, I believe I know what I'm doing here. OK. There's that, and there's that. I'm going to put that in here, and now it should work. OK. There we go. OK, so here's what it printed out. Let's see, hang on. There we go. OK, so here's the Rick Astley first cry for help. It printed all the lyrics, right? Lyric. So it said there's the artist, there's a title, and then she's taken my time, convinced me, blah, 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 right? That's all the lyrics in a row. And I put the little angles here just to show you that's the end of each word. And that reads it in and gives you those individual words and put it into a vector that we then printed out. OK? Go look at the code yourself, and you'll be able to see how it works. But it'll show you the idea. And this should actually get you started on like reading the database in if you're having trouble with that, and how to maybe structure it into a song class. OK? I wanted to give you the ability to do that if you're still struggling on how to begin there. OK? Questions on the iterator for right now? Yeah. That's a good question. Is it like a for each loop? It is kind of like a for each loop, which we want to explain to the class what a for each loop is? Yep. For each object in your list, you're then doing what you want to do with it, right? It is exactly like that, really. This is saying the object in this case is the word, and the word happens to be of a type, a pointer to a vector string, right? Rather a string, which is the type. And so that's the object. And that object could be anything, right? It could be the song, it could be the lyric, it could be the whatever. And that's exactly what it's doing. And then instead of saying, oh, I'm going to reference it by index, you're referencing it by the object. So yeah, it's a for each is a good way of thinking about it. Yeah. Good question. Yes?
So,
Hobby.
what it's doing is adding one to the pointer value, which is the next piece of memory.
Absolutely. It's adding 1 to the pointer value. Yeah, and it knows. So the compiler knows how big is a string. Like how much memory does it take? And it has string, 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 right? Now, keep in mind, it's not the number of characters that decides that. It's the object itself. The characters are actually stored somewhere else in memory. Like it's a misdirection a little bit. But you've got a string, 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 and it knows it goes, the next string is here, the next one is here, the next one is here, like that. So exactly what it's doing. It's walking through the objects, like it's going one to one to one, the next objects. Good. Yes, Marcus.
I'm curious why this is the preferred method.
Yeah, why is this the preferred method? Anyone want to answer that? Anybody have an idea why this might be better than the other method? It's more generic is what it is, right? It's a generic way of doing it in that you can always go through it like this. By the way, there's also ways to go reverse iterators, or you can iterate through a hash table if you wanted to. That's a little weird. Or you could iterate through a set where there's a function that's built in on how you get from point A to point B. It's not just an index. For a vector, it really doesn't matter. Vectors we know are in order, in memory, and we're going one to one to one. But let's say you had a linked list. You could do an iterator through a linked list. You can't do a bracket notation for a linked list. You have to know something about the nodes. But if you have a linked list with an iterator, the iterator under the cover says, what's the next node? And it picks it out. What's the next node? And it picks it out. It might be over here, over here, over here. So that's more generic in that sense. OK, good. Yeah?
How would you make an iterator for it?
Good question. That's probably a little beyond the scope right now. But really what you do is you say, how am I going to, it's basically a pointer to the type of object that you might be going through. That's really how it is. And you can, all you have to do is actually create another function that's called iterator that returns some value. And in this case, it's going to return a pointer to the next word. That's all this one does. So it's actually not that hard. It's just you have to dig in a little bit and see how you do it. But you just create another function, and it's called iterator, and that knows how to deal with these sorts of iterators. And you have to create a begin, and you have to create an end, and you have to, there's a little bit more to it. But it's not that hard, really. It's just there's specific rules for it. Okay, good question. Okay, yeah.
So
Morgan.
In a for each loop, you assign each value of the array to like a separate object, which you then use to look at it.
Yes.
You can't actually change the array itself that you're copying from. Can you change the array that you're going through with
Yeah, good question. Good question. I believe you can. I believe this is simply a pointer to the actual location. So if it's of a type that can be changed, then you can change it. Some of them are not. Like you can't actually change strings directly like this. You have to replace it with another string, and I'm not sure it allows you to do that, but it may. If it's a pointer, it should. But yeah, good question. It's not a constant. Well, you don't necessarily have to have it be constant, I don't believe. Yeah, good question. Okay, anything else on the iterators here? You really won't have to worry about iterators unless you do one of the next things that I talk about, but you probably won't have to worry about it. I just wanted to introduce it because you'll see it a lot if you do more C++ programming. Okay? All right, that's the iterator itself. That's the first element. That's just after the last element. Okay? And that's how you increment it. And there's how you dereference it. Woohoo. OK. Where else could we use vectors? Well, maybe some of you guys are actually thinking of making vectors like an initial dynamic array of songs. Not sure that's necessarily the best way to do it, but you can. Okay, but you could do it with a vector of song pointers to songs. Let's say you wanted to say, I don't know, keep the top 10 hits for a song, right? If you're doing a search for it, well, a vector of song pointers would do that for you, right? Let's say each word in your dictionary has a vector of songs that it knows that word exists in. That would be a good use of this vector of songs. So each word has a vector that says, OK, each word has a vector that says, these are the songs where this word appears in. And then you can go deal with that as you go along. Okay? And then you'd push back a song, right? And the song in this case would be a pointer to a song. You could also have it push back the actual song. but that's going to take more time instead of the vector, instead of the pointer, because it has to copy all the bits from that. So we are trying to save some time here if we can. Okay, question?
If we wanted to do the sort like the ones we did for our last assignment,
Yes.
the vector,
Ah.
how would that work?
Let's see. Maybe it's in the next slide. It's not quite in the next slide, but it's a couple slides from now. You can sort vectors relatively easily, actually. In fact, there's a built-in sort function. I think it's quicksort, actually, that you can use on vectors. What you have to do, though, is you have to decide what part of the object gets sorted. If it's strings, no problem. If it's songs, right? Remember what songs were, right? Songs were here. What's going to get sorted here? Are you going to sort by artist? Are you going to sort by title? Are you going to sort by lyrics? You know? Now, this is probably not the best idea because you're not going to be sorting by song. Well, you're not going to be sorting by song. I'll give another example where we do a sort on it. In fact, there's code online that I wrote this morning that does exactly that. Okay, good. All right. So, but we'll get to the answer in a second. All right. Vectors can store pointers too. They can store anything. That's the point. Okay. You might want to have a trie. For those of you using a trie for your data structure, right? A bunch of people are. You might want to do it this way. I put a note on Piazza on how this might be important to do. Do a vector of nodes. That means you don't have to create all 36 nodes at once, right? And especially if you're doing a node pointers, it's going to be a relatively small amount of information. It will only create a minimum size for you. In fact, if you wanted to be really clever about it, you could do the node with children and say, just give me one to start at a capacity of 1, just in case I happen to have one, right? You could do it that way, because there is a way to declare a vector such that you get a capacity of 1. Might not be a bad idea if you're trying to save space in your overall trie, because a lot of combinations like Z, Z, Y, X, L, or whatever is not going to be in the word list, right? So maybe something from AC/DC or something. I don't know. But anyway, did you hear that AC/DC is like disbanding? It's kind of sad. Yeah. No more Akadeca. All right. Anyway, so you could do this. You could do this with your children, and then every time you get a new child, push it back onto the node or onto the vector, and then just go through and search through the vector to see if the word, if the letter exists or the child node exists. Slightly slower, but probably saves you lots of space than doing a character per node, or 36, I should say, characters per node. By the way, this is an important one for those of you who are thinking about a trie. The trie is going to have letters in it and digits, because some things like there was a lyric that says like something something 1 a.m. and the 1 is part of the word, and that's not getting stripped out. Okay, alpha only actually means alpha and numeric only. It turns out. Yeah. Ben.
Does our hash function work for that?
Hash function works perfectly fine for any string. Yeah, even with the punctuation as well. It'll work fine. Yeah, good question. Okay, so this is exactly your comment, right? Let's say you wanted to store a list of songs by the frequency of the word they contain. That seems like it might be likely for our project, right? If you have a struct that has a song with frequency, and it has a song and also the frequency in there, the song pointer and also the frequency, you can make a vector of song with freq structures, right? You can do that, and that's what's nice about being able to do this like that. This is the next one I was talking about, there is a sort function. Sorry, Bruce, you too fast on that. No, that's all right. If I go too fast, just whoosh. All right. So there is a sort function that you can use that's built in that allows you to sort these containers. Okay? You could use your own sort that you built last week. Perfectly fine. Okay? If you're dealing with container classes, it's probably a little easier to do it use the one that's already built for you. There are a couple of caveats here. Caveat number 1, you have to provide an overloaded less than operator. In other words, How does the vector know how to sort based on your structure? What would you sort by for this one? Frequency, right? So we're going to create it. We're going to create an overloaded function for frequency. It's actually not that hard to do. I'll show you. Okay? And here's the other thing. The default sort is ascending. In other words, it goes from smallest to largest, not largest to smallest. Right? So you have to be a little careful with that. It's relatively easy to get around that too. You can do two things. You can sort ascending and then reverse it, because there's a reverse function in a vector. That's nice. Or you could come up with a way to do it by the greater than as well. I'll show you how to do that too. And this code is all online on the website. Okay? Let's see how you would do that. Okay, so we have our song with frequency struct here. Okay? Here's how we overload the less than sign. We say it's going to return a Boolean. If you're saying, is this less than this, it's either true or false. We overload the Boolean operator. This is all boilerplate stuff, right? It's like you're going to have a const, you're going to have song with the frequency. It's a reference to the left-hand side and a reference to the right-hand side. Boilerplate. You're going to write that every time for this type of function. And if you do have trouble writing these, I'm perfectly happy to help you out. It's not really that hard. All you're saying now is, if the left-hand side, in our case, frequency, is less than the right-hand side frequency, return true. Because that means that the frequency of the left-hand song is less than the frequency of the right-hand song, and that's how it's going to be able to sort it. So you see how it's going to be able to sort it? You see how it's going to be able to sort it using this? It knows about less than, and it says, I'm going to use less than, and figure it out. If you overload less than, it works. Tala.
Could you also use a priority queue where the frequency is the key?
Absolutely. Yeah, you could totally sort using a priority queue, a heap sort of thing. Sure. Yep, absolutely. Yep. If you want to do it that way, that's perfectly fine. Yep. You would have to build that yourself, and you know how to do that now, so you could do it, right? All right, here's how you sort it. You say sort, and then you give the beginning iterator and the ending iterator, and that's it. And then what happens is it does it in place, or it generally does it in place. But it will then, when you after this line, the songs will now be sorted by the frequency. Ta-da, we win, right? And it's quick sort, and it's going to be a good sort. Hundreds of people have looked at this and made sure it's a really good sort. They're going to use all the little tricks that you might not have known for your homework assignment last week, right? Yeah.
So it has to sort it when it's in a struct.
It doesn't have to. It will, as long as whatever object you have, in this case songs with frequencies or strings or whatever, has a defined less than operator, it will sort it just fine based on that less than. Now, for strings, it's already built in. It's alphabetical. Which one comes first in the alphabet is less than the one that comes later, right? For numbers, they're just numbers. You know less than or greater than. So for most of the things are already done for you. For your own struct, not done for you. You have to come up with your own. But it's 2 lines long. It's not that hard. It's just you got to know when to do it. Okay, good. If you forget to do that, it'll give you an error. It'll say, I can't figure this out. The error will probably be cryptic, but it will give you an error regardless. Okay? Yeah.
Where would we put that definition?
This one? It is outside the structure, kind of floating anywhere else in the file. Yep. It's got to be before the sort happens, I believe, but that's it. Yep. You would probably put it in this one. You would probably put it in wherever you define song with freak. You'd probably put it in that same file, yeah, or in the associated CPP file. Yeah. Good. Okay, that's how you can do sorts. You can sort, as I said, by the greater than as well. I show you how to do that in the code that's online. Okay. All right. Okay. Any other questions on vectors before we kind of go on to the next little bit? Yeah.
Do you have to, does it delete the memory itself?
Oh yeah, it does delete it by itself. Yeah, it will if your vector no longer exists, it knows to do all the deletions. Now, your own structure should have a destructor as well if it's going to delete it properly. But otherwise, yeah, it will call delete on it will call your destructor for your class if you have one. Yeah, good. Other questions on vectors? Again, the code is online. I'm perfectly happy to walk through it with anybody, but it should give you a good starting place for either sorts or for setting up your classes with vectors. Okay, and hopefully it'll be helpful. All right. How is it actually possible for classes to do this? Right? This is like going a little bit more into the weeds. Okay? You may never actually worry too much about the next little topic I'm talking about, but you should understand it, and you should understand it so that you can read documentation about it. That's kind of the trickiest part, right? Sometimes it's like, how does this work? I have no idea because I don't know how to read the documentation about it. Hopefully this will help a little bit. The standard template library is called a template library because we use templates. Okay? These templates are, here's the structure for building a class that uses any other type. Okay? I have an example here that will walk us through what that actually means. Okay? I'll walk us through how that actually works. Let's say we want to create a little calculator, and our calculator does the following. It adds two numbers and it multiplies two numbers together. This might be our first attempt at this, right? This is not a template. It's a regular old function. You've built this a zillion times. You have a class, or it's a regular old class. I'm going to call it calc1. It's going to be public methods of multiply and add. They're both going to take integer, 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 return integers, standard stuff, right? Really simple. Your multiply function multiplies and returns the value. Not hard. Your add does the exact same thing for addition. And it works fine. You do cout 1 plus 2 and you end up getting 3. And you do cout 2 times 3 and you end up getting 6. Perfectly good, right? Here's the problem. It only works on integers, right? If you wanted to go do it with floats, you wouldn't get a floating point answer at the end. You'd get an integer, and it might not even work, but it would probably try to jam it in there, but it wouldn't do what you think it does. Why? Because you've hard-coded int, all those ints, right? We don't want to have to do that. We want our function to be able to be used with integers and floats. So you can do this. This next page is your first. It's like your hello world template. Okay? Let's walk through what this says. You start with a template and you say, I'm creating a template. Okay? And then it says, and then you say type name. Sometimes you will see it called class. They've changed it to be type name because that got confusing because they used class in other places. Probably the first good decision I've seen in a while from like people who make these compilers, right? Type name says what type do you want to put in here? It's not a specific type. It's a generic type. We're going to call it T. A T can be an int. It can be a float. It can be a string. It can be a struct. It can be whatever you want as long as it's a defined type somewhere. What have you done now? You've replaced everywhere you had int before. You've said, let's make it my type. Whatever my type is, I'm going to replace there. So this says multiply two variables called x and y of type T and return type T. Is that hard to understand? It's saying make it generic. Whatever your type is, do it. Yeah, Eliza.
How would you be able to add or multiply, like, say, structs?
I don't know. That's a good question. How would you add or multiply structs? It's going to work for the types that have add and multiply defined, right? Good, very good question. Keep that in the back of your mind for a minute. Okay. So does this work now? When we now create a calc2, this is the calc2 class, we do calc2, angle, bracket, float, and we say we're going to use floats now. And then our calculator works on floats. Woohoo! Right? If we wanted to create a calc2 with integers, we could create a calc2 with integers. Woohoo! Right? That's the whole point. Now it works with that. Okay? We've solved it for other numbers. Does it work for other things like strings? That's a good question. Can you have a calculator that adds two strings together? What would a calculator do that has two strings? What might be one thing it would do? If you have A, B, C, and D, E, F. Yeah, it concatenates them. That's actually well defined for strings. Add a string to another string, you get the whole thing scrunched together into one string, and you get it back. It's actually defined, right? How about multiply? What does it mean to multiply two strings together? if you try compiling this, like as it is, right? It gets through this and goes, no problem, I can add strings. And then it gets to this and goes, wait a minute. It says, I don't think I can multiply strings. There's no such thing as multiplying strings. So then are you done? Or you say, well, you can never multiply strings? No. You define a multiplication for strings. Whatever you want. That's the beauty of this, right? You say, I'm going to think string multiplication means this, right? And you define it. I was thinking of an example of this. So you know how you guys haven't taken linear algebra yet, but you've probably taken physics. Have you done the dot product and the cross product for various things, right? That is a function based on numbers that takes one piece at a time and does something to each piece and comes out with an answer at the end, right? So it's kind of like, it's a different function. It's not a multiplication. Well, it's kind of a multiplication, but if you're doing the dot product on 3 vectors, it takes like the first piece of the first one, and the first piece of the second one, and the first piece of the third one, and multiplies all those together. And then the second piece of the first one, and the second piece of the second one, and the second piece of the third one, and multiplies all those together. That's how the dot product works. So they've defined that function for numbers that are vectors, right? You can do the same exact thing if you want. So this morning I thought, I don't know what it means to multiply strings, but let's say that I can do this. I'm going to say that multiplying strings is the following. String 1 times string 2 is interleaving. That's what I'm going to say. I'm going to say if you multiply 2 strings together, you're going to interleave them. So ABC times DEF gives you ADBECF. ADBECF. Does that sound legitimate for, we can call it that, right? We can say multiplication is that. Define it any way we'd like. Awesome. Right? When you define a multiplication, what did we see about 2 slides ago that is a very similar sort of thing to do to an operator? Overload it, right? You're going to overload, in fact, it doesn't even exist yet for strings, but you're going to overload the multiplication operator, right? OK, here's how we might do this. Now, this actually looks more detailed than it really is. All I'm saying is interleave those 2 strings. OK, look, string operator star, that's my overload. Here's my string left-hand side, constant string right-hand side. It's exactly the same as that less than thing we just did. Remember boilerplate stuff? It's very similar. It's going to take a string, 2 strings. It's going to multiply them together. It's going to return a string. And here's how it's going to do it. It's going to walk through both strings. Whatever the maximum one is, you're going to walk through that many times. And you're going to get to, and this may not be the most efficient way. I threw that together at 8:30 this morning, right? But if you walk through this, you're going to walk through and then print out each character in turn of the one from the left, then the one from the right, until you get to the end of one of them, in which case you just print the rest of the remaining one. So you interleave as much as you can and then print the rest of the longest one. Does that make sense? OK? So I just defined multiplication for a string. And then at the end, you return the actual string itself. Not too bad. OK, I've defined the multiplication. When we go back and use this definition, this one still works. Prints out A, B, C, D, E, F, because it's A, B, C, D, E, F, because it's concatenating it. And this one works. Right? Now it works. What is this going to say? I think I did it right. Hope I did. That's a space, by the way, and there's a space before that letter. Oh! What's it say? A secret code, right? So if you break up your strings into 2 things, right? You can end up doing something like a little bit of coding, right? Hey, here's what we do, OK? So Elaine and I want to share something, a secret, right? And we only want to be able to know the full secret like when we get together. Like, so if one of us gets captured while we're a spy, We can't, like, the message isn't, we both have to reach the place to get the message there, and otherwise it doesn't matter. So I take this one, right? And Elaine takes this one. And we go our separate ways, and we both finally meet up at the secret spy headquarters, right? And we put our message together, and it says a secret code, and it tells, like, the answer to, like, beating the communists or something, right? So whatever, right? So that's that. But anyway, look, you can do this by, all you need to do is overload that idea. Okay? Questions on this? Yes, Avita. Oh, good question. How does it know it's a multiply and not a dereference? It's all context, right? One of the things about C++ is it happens to be a context. No, it's not a context-free language. It needs to know something about the context. It's actually more explicit than that. But when it compiles, it knows, hey, guess what? If I see a multiplication here, it can't, or the star symbol here, because it came after another variable, it can't be a dereference. It doesn't make any sense, so it's got to be a multiplication. It goes through a hierarchy of kind of a heuristic of how to figure it out. Yeah, good question. Yeah, good question. Other questions on this? When are we starting our spy company? Anytime soon? All right. OK, so hopefully that gave you a little bit of information about vectors, a little bit about the possibly seeing type like templates, right? If you see something like this, type name T, that means that's the type that you're going to be sticking in there. Okay? And you kind of get a feel for how C++ does this. And then you can see you can do fun stuff like come up with secret spy codes. Other questions on this? No? OK. Let's see. Anything else on this? See, templates really important, are really powerful. You probably won't use them much. I mean, like, you probably won't build many templates. It's not that often that you need to do something for many different types, but you should be able to understand them and use them. And you should use iterators, definitely. Okay? There's a bunch of references here. The vector reference is a good one. A bunch of Wikipedia articles, good template tutorial, Idiot's Guide to Templates. All right. All right, if there are no other questions, I'll see you guys Monday. Next Wednesday. Next Wednesday, or Tuesday in lab. Yeah, the Monday labs will be the following Monday.